Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Very happy to have again Janko Grabner from University of California, Davis, giving his second lecture here, and this time the topic is snowflakes.
Thank you very much, Hunter. So when I noticed some of you pulling your notes up, I got reminded that I gave a talk once to the more general audience that I'm used to, namely audience of art. Can you turn your microphone on? Oh yeah, sorry. Audience of art students at Davis. And they actually managed to take notes by sketching the snowflakes very quickly as I was talking. So there is some amazing skills that people have. Anyway, so this is like before the movie starts, a little slideshow. Okay, so also another advantage of this work is that one could make Christmas cards. This is what I did for last year. Also, this was used for Christmas cards by our university, by American Mathematical Society, and so on and so forth. So this work is in high demand. Unfortunately, I wasn't ever able to make any money of that. I got once an offer from an air conditioning company. But then I asked them how much you're willing to pay, and they never heard from them again. So,
They know you're not serious.
right, exactly. They could tell I wasn't serious. Anyway, so this will be really a fun talk, all right? I apologize if you're, if the word theorem and proof is going to be sorely missing from this talk, but that's how it's going to be. What we're going to talk are two things, really. So when mathematicians think of snowflakes, we often think about some curves that are generated recursively and give you some fractal. They have some fractal structure. Or we think about snowflakes as real objects that fall from the sky in winter. And we will talk about both, starting with a little bit of history from the beginning. I should say this is joint work with David Griffeath. The summary that I'm giving today is from like five or so papers with him. I also want to always give special thanks to Ken Libbrecht, who is at Caltech and who is the world's foremost expert on snow crystals. And you will see many of his photographs. Another photographs that we used are done by electron microscopy at Department of Agriculture laboratory in Maryland. They call it electron microscopy unit Snowpage. And they use a different method to photograph snowflakes. They first coat them with gold dust so they're not transparent. All right? Snowflakes, of course, by nature are made of ice, so they're completely transparent. So if you see a structure and the snowflake is a three-dimensional object, typically, you don't know whether the structure is on the outside or on the inside. So that was useful, very useful to us in that way. Okay, so these are some of the first published pictures of snowflakes. This one leaves a bit to be desired by today's standards, but nevertheless. The study of snowflake is credited, the beginning of the study of snowflake is credited, of course, to a Chinese scholar, Han Ying. But in the West, really the first pictorial description, such as it is credited to Olaus Magnus in 16th century. The first real picture, pictures of snowflakes that really do look like real snowflakes are due to Robert Hooke. in 17th century, who of course knew how to deal with microscopes and obviously looked at them because they're actually quite good.
So can you see the hexagonal symmetry without a microscope?
Probably. Well, you can. There is.
Naked eye.
Yeah, you can with the naked eye. Yes, you can. Yeah, if you have a good eyesight, you can. But yeah, I mean, it's much trickier. Especially, I mean, you can see the hexagonal symmetry, but to see this, kind of more refined structure is much more difficult. Okay, of course, the most famous early treatise on snowflakes is by Johannes Kepler, who wrote a treatise on the six-cornered snowflake, and also was thinking about why this hexagonal symmetry, and was putting forth a theory that this is due to crystal structure of ice. This is, an amazing, really, insight for somebody who had no idea, really, about molecules or atoms or anything like that. So it's also, Johannes Kepler was a deeply religious person, so he was, a bit struggling with that, clearly. Sorry? Yes. He thought all the living beings have souls, but snowflakes kind of not, although this took some thought for him to conclude. All right? So I don't know, this is not typically well known. So I think the book is called Treatise on the General Method or something like that, a philosophical work by René Descartes. Had a few appendices. One of his famous work on geometry. All right. Another was on meteorology. It's called Meteor. He wrote this paragraph that you don't really need to read. I can just tell you that it's very difficult to understand what he's trying to say. He's obviously trying to imagine how the snowflake grew to be so intricate. And that's probably true because they get tossed around a lot. That's what he thought. All right? So, so that actually is the point of view that prevailed up until very recently. And I claim this doesn't make any sense, this explanation. All right? So, if we fast forward a bit to the late 19th and early 20th century, the first person who tried systematic classification of snowflakes was actually an amateur scientist, a Vermont farmer called Wilson Bentley, who tinkered with a camera and a microscope to create very many images of snowflakes that he collected when they fell down. He published several books which are still in print. Those are kind of classical books on snow crystals. The first scientist who seriously studied snowflakes was Ukichiro Nakaya, who was a nuclear physicist who apparently couldn't get grants to support his laboratory and decided that he was going to, study snowflakes instead. He was the first one to be able to actually grow artificial snowflakes in the laboratory. So we also grow artificial snowflakes, but in a whole different level. All right. So he wrote. He is the writer of the classic about snowflakes. This book, Snow Crystals, Natural and Artificial, 1954. All right. So let's talk a bit about mathematical idealization. So as I said before, when one says snowflakes in a mathematics talk, usually one is prepared to see a study of objects that look like this. All right. So this is a Koch snowflake more than 100 years ago, introduced more than 100 years ago. And it's just introduced by, adding a triangular bump on every straight line. And starting with a hexagon, adding a triangular bump. Or with a triangle and adding a triangular bump, and then continuing that until in the limit you get a fractal curve. All right? So this the flow snake, as it's called, it's called flow snake because it has the opposite construction. Instead of adding a bump, you cut. You cut inside on any straight line. You see, start with a hexagon, make a cut, make a cut, make a cut, and so on. All right? So then you end up with something very similar. This pentaflake is, you do this. You start with initial pentagon and then do these incisions. So it's very similar. And then this consists of 6 pentagons. You do these incisions and so on up to the final picture, which looks like that. So see, they all have this infinite construction, recursive construction, and some sort of fractal limit, and in an appropriate sense. A completely different way of creating a kind of snowflake picture, though it looks much less like a snowflake in popular mind, is by diffusion limited aggregation, a famous process started in the 1980s, and of which is still, there's many open problems for probabilists to work on. So what you do is you start with a single, if you wish, frozen particle at the origin, and you just, at every point, once you have an aggregate of frozen particles, you start a random walk far away, and you let it diffuse, and then when it reaches a neighborhood of an already frozen particle, it sticks. All right? So this is a process very difficult to understand. Maybe many of you know the opposite process, which is called the internal diffusion limited aggregation, where the particles kind of originate at the center and move outwards and stick when they hit an unoccupied site. That is a much simpler picture because it's actually, instead of making less and less regular structure, they create more and more regular structure. All right? So we'll return to this theme later on. Witten and Sander, yeah.
No, is Witten Ed Witten?
No, I don't think so. This is too early for him. You really?
No,
That's possible. I forgot, actually. Could be. Could be.
Definitely not too early.
All right. Okay. So I actually don't know that. Could be. Could be Ed Witten. It's kind of not in his line, but it could be.
Not in his line.
Yeah. Could be. All right. So this is our work that we did is really a successor of a small and obscure paper by one of the pioneers of the field of complexity and chaos, Norman Packard, who wrote a, just maybe 5-6 page paper in 1984, where he proposed 2 models for snowflake growth. One is a variant of the diffusion limited aggregation that I just described, and another is a class of cellular automata on a triangular lattice T, and that's the triangular lattice, for those of you who don't know it, but I presume many of you do, where basically you just add occupied points to a set of already occupied points. Occupied would be the same as frozen here. And the rule is, I'll introduce and give you a few movies with the rules later, but the rule is simply that point looks at an unoccupied point, looks at its 6-point neighborhood as drawn in this picture, and counts how many already occupied neighbors it has, and depending on that, it decides whether to become occupied or not next time. All right? And basically, he observed that if you for sure become occupied when you see exactly one occupied site, but for sure do not become occupied when you see exactly 2 occupied sites, then this growth kind of favors the tips. So you create, as you will see, some sort of structures which look like snowflakes. So, and that he thought that this is true for real snowflakes too, that the growth kind of favors the tips. So I should say that then this was developed a bit by Reiter recently, about 7 years ago. And of course, the cellular automaton approach was popularized by Wolfram in his book and various papers when he thought this was the last word on snowflakes.
Is this a monotone process?
It is a monotone process in the sense that you add more and more occupied points.
So nothing dies?
nothing dies. In that sense, it's monotone. But it's not monotone in the sense that if you add one more occupied point somewhere, you're going to always get more occupied points. So occupied points don't necessarily help you, as you will see. All right. So here are pictures from the Packard's paper. They don't look like they're going to win any Christmas card contests just yet. But it turns out that this is actually a very promising idea, as demonstrated by Reiter. All right. This is for a person who's seen a lot of snowflakes. This is a promising picture, but it's not quite right. There is too much branching. Also, it's two-dimensional. All right. So here is, I mean, at the very beginning, kind of the stellar automaton looks a bit better than the DLA. So this is a Reiter's. This is a Packard stellar automaton, and this is a picture of a real snowflake from Libbrecht's collection. So they look a bit similar. All right. For reasons that we'll see later. Why? Okay, so when we do simulations, and during today's talk, it's very fortunate since they don't make computer screen where the pixels are arranged in a triangular fashion. They would be nice for this sort of thing, but they don't exist. So you have to kind of deform that lattice a bit, and it's very fortunate that you can actually do it. All right. So the usual rectangular lattice with the added diagonal connection is actually the same as the triangular lattice by a deformation. You see that, right? A linear deformation. All right. So let me just explain the notation for you. I'm not going to go into any detail. So these are the Packard cellular automata that I was describing before. So hex 1 is, so it's they're monotone. We call them, they solidify. So once occupied, the site remains occupied forever. And you write hex 1 if the only way for a site to join the crystal if it sees exactly one already occupied site, and 1, 3, 5 if it sees 1, 3, or 5, 1, 3, 4, and 1, 4, 5, 6. All right, so these are called occupation numbers. So let's look at some movies. All right, which we have. Okay, so this is hex 1. Okay, so let's see what it does. So from a single occupied site, and you just use this rule that you look in your neighborhood of 6 points, and whenever you see exactly one occupied site, you become occupied. So you see what happens. So this kind of alternates between between this kind of fractal boundary and full hexagon. So if you want the full symmetry of the triangular lattice, you have to deform it a bit in your mind or think that you're watching this from the side. All right. So in between this, which looks kind of that it has fractal boundary, and then it creates a full hexagon, and then new nuclei sprouts from the corners, and so on. So this you should also note that if you look at this picture a little closer, of course, not all points become occupied. There is some sort of density of of occupied points. So let's look at another picture. Another rule, 1, 4, 6. So 1, 4, 5, 6. I'm sorry, 1, 4, 5, 6. So it looks very similar, right? The kind of macroscopic picture looked from far away looks very similar, but if you zoom in, you will see that all sites become occupied. So that's the conjecture you would make, that every point eventually becomes occupied. So remember that conjecture. All right. So in this particular rule. So let's just, while we're at it, let's just look at two other movies where you change the neighborhood a bit. So instead of hexagonal neighborhood, you use box neighborhood, which is instead of 6 points arranged in hexagonal pattern, you look at the nearest 8 points, and exactly one rule. Let's see what happens. So similar picture, except a different geometry, right? However, let's just look. So this rule, if you start with a different initial set, also creates this sort of regular periodic pattern. So, okay, so these are the movies, just to remember later as we discuss the results. Okay, so first, this is one of my favorite quotes. All right, of course, these Packard rules were widely known, and Stephen Levy, who is a science writer, very well-known science writer, wrote a book, Artificial Life, in 1992, and in which he said an elementary school child could look at any of the gorgeous pictures of computer screens in Packard's collection and instantly identify it as a snowflake. So why is that funny? Well, that's funny to me because people most people have never seen a snowflake, right? A real snowflake. Well, they have seen snowflakes in Christmas ornaments like this, which they call snowflakes, or the ones which you cut from papers and so on. And they may have nothing whatsoever to do with real snowflakes, like this one, for example, which has 8-fold symmetry, which no snowflake ever has. All right, so they would instantly identify it as an iconical snowflake rather than a real snowflake. So these Packard snowflakes have the nice virtue that you can actually prove theorems about them. And the reason you can prove theorems is because if you look at the points that become occupied as soon as they possibly could, all right? So those are the black points here in this picture are points that are occupied as soon as they possibly could. They're occupied at the edge of the light cone, if you wish, all right? So these are the points that the dynamics can possibly, theoretically, influence at time t, and at that time they become occupied. So they create this sort of what we call additive web. So they really run an additive dynamics of the type that I was discussing in my previous talk. And the boundaries here are impenetrable, all right? So they divide the space into regions which don't communicate with each other. And this creates naturally a renewal structure. And that renewal structure is enough, via the use of the renewal theorem, is enough to prove that the density, for all of these rules, the density exists. So it's a well-defined number. You can imagine the definition. It's a natural definition. So the density is a well-defined number, and it's independent of the initial seed. All right, in all these Packard snowflakes. And this is surprising because unlike stochastic, unlike random systems, cellular automata very rarely use memory of their initial states. Right. So, for example, I've shown you a picture of a different rule with the different neighborhood, which does not lose memory of its initial state because it has two different densities from two different initial states. And you can also, the renewal theorem actually allows you to estimate, or in some cases, compute exactly the density values. And here are the numbers. Note that, so this was the rule for which we conjectured that every point eventually becomes occupied. Yes, it has density very close to 1, but not quite 1. And one could prove that. However, if you look at this rule on this screen, you'd never see the first permanently unoccupied point, because that one happens at time about 10 to the 9th. So at about time a billion, the first pixel that never fills in occurs. So you would never see this unless you analyze this rule mathematically. Even, there exist programs which could simulate this for this long, but, display is the problem. Where would you look? So since you don't have the screen this big, it's very difficult to see. Anyway, this, if you want an open problem, is so for some of these rules you can show that density exists, but they have, for example, these two, we don't know whether densities are equal, although we suspect they're not.
So are those simulations or are those?
These are rigorous results. All right. So see, within plus or minus. All right. So this is actually rigorous. All here is rigorous. So therefore, we cannot rigorously exclude the possibility that these two are not equal, although they probably are not. Okay, so let me just, the next slide kind of tells you that Packard snowflakes are not going to be very good. Yes?
So one question. So when you say row 1, 4, 5, 6 is
Yeah.
strictly less than 1,
Yes.
you actually have a bound.
Very, very bad bound.
But there is one.
There is one. Very bad. Too
minus.
embarrassing to write down. Yes. Less than
Perhaps
1.
you can say
Less
it's
than.
at least something like 10 to the minus 9, right?
No,
or-
it's
or
even smaller than that. Yeah. Something in the order of 10 to the minus 10, or 12, or something like that. All right. Yeah. Away from
But
one.
you have proved that various densities, when you say they are the same, like 1, 3 and 1, 3, 5.
Yeah. This is.
1, 3, 4 equals 1, 3, 4.
Yeah. So these are all proved. All right. All the estimates here are rigorous, and equalities are rigorous. All right. Just this we don't know whether they're different.
And 1, 4 equals 1, 4, 5 would be that no matter how you start.
Yeah, it tells you how you add points. So 1, 4,
No,
6.
of
Yeah.
course, it gives you the rule, but do you mean that no matter how you start, you get density?
Yeah.
row
As soon as.
row 1, 4, 5, and it seems that it's the same as 1, 4.
Yeah. As long as it's a finite seed of occupied sites. Yeah.
I mean,
Indeed.
that was the theorem, right? For any finite seed, the density is the same.
Yes.
So it's enough to
Yeah.
find a seed where they.
Yeah. If you find a seed where the density differs, yes.
Yeah.
Or to different seeds, right. All right, so the next slide will tell you that Packard snowflakes are really not that good to simulate real snowflakes because they're extremely sensitive to random perturbations. So this is actually related to the open problem I mentioned 3 weeks ago. So if you, so let's say you become occupied for sure if you see exactly 1 occupied site. But if you see 2, you flip a coin with a very small probability, P, and if it comes out successful, if the flip is successful, you become occupied, and you will see that fractal shapes completely disappear and you generate just a regular growth. Now it is true that many snowflakes are just plain old hexagons, but obviously that's not all to the story. So all there is to the story. So you have to start over from the beginning if you think about modeling real growth of real snowflakes. So in order to do that, let's familiarize ourselves a little bit more with the real snowflakes. So this is a sample of Bentley's photographs. So the one thing you observe, well, first of all, you observe that, sure, there are snowflakes which kind of have a familiar branching pattern that we see, but also there are lots of plates, all right? So they kind of, snowflakes kind of exhibit this tension between branching and, as they call, this is a real word that they use, faceting, all right? So they create these sort of regularly shaped facets. And also the other thing that you observe is those, another technical word, hieroglyphs, patterns that you see on snowflakes, all right? That, you want to know how these are formed, all right? These are called the ridges. These are called ribs, all right? So there's all this terminology that one learns. So, okay, so here is the main scientific puzzle about snowflakes. So the fact is that, what snowflakes do really is, the main accepted explanation about how they grow is that they do grow by diffusion. So they're somewhere in the cloud, and the particles in the clouds just diffuse. So they aimlessly wander around, and they stick upon encountering the crystal somehow. So how do they stick? They basically stick with some probability when they hit a point on the crystal. So how do they stick is really unknown. All right? It's really unknown to the extent that this picture that I'm going to explain in a second is not explained at all. So clearly the rule about how they attach, how the water vapor molecules attach, And by the way, so the important thing is that the growth is directly, the snowflake formed by vapor directly freezing. There is no intermediate liquid stage. All right? So the way the vapor molecules attach is it depends on the temperature and depends on the atmospheric pressure. All right, and here is how how it depends on the how the growth depends on the temperature. So for very low temperatures, you see snowflakes which are basically flat, the snowflakes that we used to see, right? Nice hexagonal plates with some branching. Then you increase the temperature to -5. So this was -15 degrees centigrade. You increase the temperature to -5 degrees centigrade. You see certainly something that no school child would ever identify as a snowflake, right? You see a three-dimensional pencils, basically. All right, so they grow almost exclusively in the third dimension. And then you increase temperature to -2 degrees centigrade, so even a bit more. And so snowflakes turn to be, smaller, but still basically the same shape as at the beginning. So there's this double phase transition that is a real I don't know if mathematical modeling can ever resolve this, but it's a real physical puzzle about, what temperature actually governs to make this difference.
So is
Yeah?
there any phenomenon where if you're very close to the phase transition point, things are more complex?
Well, certainly we see that in our model, but
But in
I suppose I would suppose that all the most interesting snowflakes actually live on the borderline. That's what I suppose. So all that you see on pictures are actually very close to the boundary. Certainly, we see that in our mathematical model. And you'll see what I mean. Anyway, these are pictures from Libbrecht again. So he uses Photoshop a lot to make them look nice, because I also saw them when after he just takes a picture, and they don't look like much because they are transparent. So you have to enhance the edge, add a little shading, and so on. All right? So you of course, see the same message as we saw from Bentley's pictures. All right? Lots of branching, but also lots of plates. So there is a tension there. These are, one of his successes was that they were on stamps in 2007, well, for a New Year of 2007. Obviously, a lot of graphical manipulation here, because they look like they're made of shiny metal here. All right? So let's think about modeling a bit. So how would a mathematician approach modeling of snowflakes? Well, so we already know that basically the snowflakes form by vapor diffusing around it and then attaching. And the parameters that govern the growth are temperature, availability of vapor, vapor density, and atmospheric pressure. So the diffusion is clear. Everybody knows how to model diffusion, either by differential equations or by random walks. That's not difficult, but attachment and detachment are not understood. So this is what you do when you don't understand something. You just introduce a few parameters and you vary them until you see what you wanted to see, right? So tunable parameters. So that's idea number one. Idea number two is, well, you have 10 to the 15 to 10 to the 18 water molecules in a snowflake. And so in order to build the snowflakes one molecule at a time, you'll have to allow them to diffuse. And that's a lot of computation time and resources. Maybe nowadays, actually, it's already doable. All right? But still, it's a hassle. This is a lot of variables. Okay? So maybe impossible, I should rather say impractical. All right? So, well, then you say, okay, so I can diffuse molecules by random walk, but also I can, just make them obey the heat equation, so I can use PDE models. But then there is a problem there too, because snowflakes are hardly irregular objects. So it's certain that any PDE model will encounter an array of instabilities, and you'll have numerical problems solving, continuing the evolution past those instabilities. All right? So basically, the idea is that you can try something in between called the mesoscopic model, where you divide the space into units of essentially diameter of 1 micrometer, which would make, which would make this many water molecules. So, the crystal will be made out of these units, and there will be hexagonal prisms, as you will see. And the final crystal will have 10 to 1,000 times larger diameter, which corresponds to about the real size of the snowflake. Okay, so this is your typical mesoscopic unit. It's a prism like this, and it has, so it's arranged in the two-dimensional direction is arranged in a triangular lattice, and it also has vertical neighbors like this. So every prism centered at a point there has 6 horizontal neighbors and 2 vertical neighbors. All right, so the lattice is triangular lattice cross Z. And also, so this is the blue structure here is a small crystal, which consists of these mesoscopic units as drawn, and these are boundary prisms. All right, and the numbers here tell you how many neighbors they have in each direction. So this one on top has 1 neighbor in vertical direction and no neighbors in the horizontal direction. This one has 2 neighbors in the horizontal direction, 1 in vertical. This one has 3 in the horizontal and 0 in vertical, and so on. All right? So the idea is that, let's just, the idea is that these prisms, when they're away from the crystal, what happens is they just exchange mass by diffusion with their neighbors. When they're close to the crystal, they also contain partially frozen mass. All right? And when that partially frozen mass exceeds some threshold, they join. All right? So the threshold for joining depends, however, on the boundary arrangement, as in the picture. So it's easier. It's going to be easier to join if you're in kind of a concave part of the crystal than when you're on a convex part of the crystal. So this creates a basic tension in the growth of a snowflake because the tips of the snowflake will be favored because they extend further into virgin territory of vapor. All right? So they kind of will, they look like they will be able to grow faster. On the other hand, the water vapor that gets into a concave part of the crystal will have an easier time to attach. All right? So, in that that's a regularizing force. All right? So the fact that the concave parts have an easier time catching the vapor, and the fact that the tips see further into the vapor creates opposite effects. All right? So and then this in some sort of fairly obvious way, after you've made all these things, you create, all of these units. I can just go to the next slide. Each of these units contains 2 fields. One is the diffusion field, and the mesoscopic units, mesoscopic prisms away from the crystal, only contains the diffusion field, which only exchanges mass with the neighborhood. On the boundary, like these red prisms, you also have a frozen field, which kind of exchanges with the diffusing field. That just means this just models the fact that particles just attach with certain probability, not for sure. All right, so this you can model with just exchange between the frozen and the diffusing field. And then after the crystal is attached, just everything freezes and nothing ever happens after that. So there is no detachment, although in reality there probably is.
And which of those parameters depends on the number of neighbors?
all of these, kappa, mu, and beta, can depend on the number of neighbors if you want. But mostly this one, really. All right? So sometimes you need a little bit if you want to fiddle. But I think it's really just enough if you make this threshold to depend on. All right, so just quickly, connections to partial differential equations. So this algorithm is a discrete version of a free boundary problem in partial differential equations, which is called a Stefan problem, which is a heat equation, right, with the boundary that also changes with time. So U is the macroscopic density. So U is 0 on the boundary, all right? And the boundary moves according to the gradient of the density right there. So that, if you've ever seen this is how it is. So you can think of this, and this W, this function W, which can be a very complicated function, so depends on the direction and depends on the gradient there. So can be a very complicated function, and presumably determines everything, except we don't know how to prove that such an equation has a unique solution or has a solution at all. So as I said, so under diffusion scaling, this morally should converge to that equation, although that's not proved. By the way, as it is in the internal DLA, the opposite process, where you have molecules detaching in a certain way. So basically, the snowflake melts, all right, or all the ice turns into vapor. So the ice gradually turns into vapor on the boundary. So a work of a PDE expert, In-Won Kim from UCLA, shows, she has the entire theory based on viscosity solutions about evolution. But it really is much easier because that doesn't create any new instabilities. Instead, it regularizes the crystal. So, all right. Another way is to introduce some regularizing terms, which is, well, I mean, it's also has some successes. All right, so let me show you. So now I've described the model. Let me show you some pictures. We originally start with 2D models. So just for one reason, I'm going to quickly review some pictures from 2D models. So these are some pictures, all right? So you see that they look a bit like real snowflakes. Here, so the 2D simulations are, of course, much faster. Plus, you can also draw the diffusion field around the snowflake. So the more darker pixels here mean thicker clouds, all right? So see the snowflake kind of exhausts. There's this aura around it, which means that there are almost no particles here. But as you go further, there are more, and they have to diffuse in order to, all right, attach. So of course, it's a problem because the particles cannot attach in the middle here. It's a two-dimensional model, but nevertheless. All right, it creates this sort of branching, what we call branching instability. It's also known in the applied math as Mullins-Sakirka instability. So you see this is a snowflake grown in the lab, and this is our two-dimensional model. This is not a surprise that something like this would happen. So it starts as a regular hexagon, and then these middles of the sides kind of fall behind, and then they fall further and further behind. Also, the tip instability, as we call it, very similar thing from comparison with the picture from a paper. So this tells you that this diffusion picture is somehow, a good direction to think in. Okay, so but it's not the ultimate because snowflakes actually are three-dimensional objects, as we will see. So therefore we started thinking about the three-dimensional model that I described. So now let me just tell you a few things about so this is very difficult to program. I spent many months doing just programming. And in particular, one interesting thing is how you're going to visualize this. And so I just used the MATLAB three-dimensional visualization for basic information. But if you want to create really attractive picture, you have to use something else so that the snowflakes really will look like ice. And the best method, in my opinion, is called ray tracing. So what that is it's a computer graphics method where you have some source of light, and the program traces how the light beams bounce around your object. There is amazingly a very good free program to do that, which if you ever need 3D visualization, I highly recommend. It's called POV Ray, Persistence of Vision. It's used for all the more attractive pictures that you will see. So let me, so the few next slides are comparisons between real snowflakes and outputs of our model. All right, so our model has several parameters, and if we adjusted those parameters using intuition that we developed by watching a lot of movies to make pictures which look a lot like pictures of real snowflakes. So these are, real three-dimensional columns that are formed in the intermediate temperature regime, and these are very easy to generate with our model. All right. So as soon as the model has preference to growth in the z direction, it's going to create either this picture or this picture. All right. So see there's this hole inside because that's how the diffusion organizes itself. So the one thing that we learned is that diffusion is actually very difficult to understand what it does. All right? Those of you who studied random walk, for those of you who studied random walks, this is not going to be a huge surprise. What a random walk does, conditioned on, not doing something complicated, is sometimes very difficult to understand. All right? So many people just plainly didn't believe that diffusion could do something like that. But as a matter of fact, if you're a probabilist, that's easy to believe. All right, so these are electron microscopic pictures. See there, they create non-transparent objects. All right, so so these are called columns, and one can easily create. You'll see in the movie a similar-looking columns, and these are what are called exploding tips. All right, a snowflake which kind of creates arms and then some widening at the end. Just regular dendrites. So these are snowflakes which one usually identifies as snowflakes. You should also note that we have these hieroglyphs like on top. These ridges on top are pretty prominent, as they are in real snowflakes. All right, here they're a little muted actually, but you can still see them. Of course, when one takes pictures of real snowflakes, it's a question as to, since the snowflake has been sitting there, whether it's not partially melted and so on. So there are all these problems with, actually knowing what is a real snowflake and what isn't. All right, plates. So I already said that, snowflakes also create kind of regular-looking combination of plates, and here you see two examples and two real snowflakes. All right, also with this kind of hexagon on top, which you can also see. Right? So you see this snowflake has almost no structure outside. And ours also has almost no structure outside, but has a rich structure inside, which, of course, you can see. Just stars, so basically arms with no branching. Okay, so let's see a few time series, if you wish, as the snowflake develops. So this snowflake starts as a small hexagon and eventually develops into this. Again, notice the plates, but also the branches. So starts as a small hexagon, then creates these ridges first, all right, and then continues, and then eventually it has a branching instability, much like you've seen before, and then eventually it ends up there. As in an instability that we observed for the first time, that we didn't know that exists, is called the sandwich instability, when the snowflake starts as usual, but then it eventually thickens, all right? It eventually thickens, and it kind of creates two plates, and all the interesting structure is between those two plates. All right? They're very common in nature, as that microscopy demonstrates. So you see this and this are kind of this type. All right, let me just show you a few ray traces, and then I'll show you a few movies. You also, in the slideshow at the beginning of the talk, I showed you that. So, so here, of course, you don't see this. These are all the structure here is inside. All right. So they are. You know, you'd have to know that from the. If I just show you this, you wouldn't know whether these ridges here and these ribs are outside or inside. Okay, so these are two three-dimensional cases. So this you've already seen. This is a column. This is a snowflake never observed in nature. And how do you think we call it? Butterflake. Yeah, butterflake, of course. Impossible to resist that word. All right. If it ever exists, you know, if you ever seen it in the winter, please let me know. This would be a huge success. But you'll see that this would have a really hard time not just falling apart. Should be extremely brittle, right? So at least falling apart when it hits the ground. So anyway, we see no reason in our model why this shouldn't exist, grow like this, but it should be very brittle indeed. So everything, you know, every little bump should just destroy it. So let's just say a few things about advantages and disadvantages of the model. So it's conceptually fairly simple model based on simple mechanisms. It exhibits, you know, realistic phenomena. It has lots of parameters, which are clearly not independent, because the real snowflakes depend on very few parameters. But so some tuning is necessary. Also, you know, sublimation means, you know, snowflakes, the ice evaporates at the same time it grows, possibly. That's not implemented. So 3D simulations are also slow so far, but we're working on that. Okay, so a few conclusions before I show you the movies, which will be very soon. So one of the puzzles of the snowflake is symmetric complexity. So the snowflakes look symmetric, but not completely symmetric. So the question is, if this is partially at least a random process, how could they look symmetric at all? And you'll see in a movie an explanation. So another thing is that there is you don't need a substantial preference for growth in one of the directions to make snowflake predominantly grow in one or the other direction. Just a few percentage is enough. Yeah, so morphology changes. So as Descartes, in that quote I had at the beginning of the talk, said, snowflakes are probably so diverse because they move around a lot. That's almost certainly not true, because at least if you accept the diffusion picture. Because if the snowflake moves around a lot, your diffusion is a slow process, all right? It's a square root of t process, right? In time t, the snowflake grows by the extent of square root of t. So if the snowflake were to move around a lot, it would basically always encounter virgin vapor around it. There would be no diffusion picture with a nicely arranged cloud of particles, which has low density on the boundary and high density away. It would all be high density. So you would have to change your model completely if you accept the Descartes point of view. All right. Also, one very interesting from a mathematical perspective question is whether actually the PDE model, even if you could prove everything, whether it would actually be better than the mesoscopic model. It is possible that they're on a, you know, up to the mesoscopic level, the processes are completely different than they are on the macroscopic level. That's quite possible. This is our greatest success. All right. No, we didn't win any prizes, but this is better. Okay. We are forgerers, right? And we've been paid the greatest compliment to forgerers ever. So LA Times published an article about snowflakes, real snowflakes, about how many times, so in atmosphere, you have to start a snowflake with some impurity. All right? Usually it starts with some impurity, like a piece of dust or a bacteria. And bacteria are quite common in the centers of snowflakes, except not this one, because this is one of our snowflakes. taken without permission, but nevertheless we were very pleased. All right, no bacteria inside. Okay.
And they don't say it's a simulation.
No, they don't say that anything. All right. So anyway, as I said, so I'm also collaborating with an artist who likes to make enormous pictures of this, which are featured in the exhibitions. But for the conclusion, let me show you a few movies, which I made. So this is a two-dimensional simulation, which is, oops, this doesn't work. Let me show you again. Oh, I should press pause. I'm sorry. Windows Media Player, not used to it. So this is a two-dimensional simulation. You see, vapor around it and exhausted vapor in the middle. If you look at this picture, I should say that before, but if you look at this picture for 1/2 of a second, then look away, you'll think this is a completely symmetric object. All right? Then, of course, if you look at this picture more, you'll see it's not. All right? So it's not completely symmetric. This branch is not the same as this branch. Furthermore, this branch is yet different. But you will see that even branches which are far away are strangely similar. All right? So this is actually a random picture. So there is some randomness in the process. But even branches that are far away are strangely similar. All right? So you see this configuration here, and you also see it here, despite the fact that these two don't communicate in any way whatsoever.
So where is the randomness?
Is in the two-dimensional case, the randomness basically is just you introduce a random amount of mass in the diffusion from the third dimension. You constantly. So this random field actually has, this gray here has actually random fluctuations in it. All right? That's where the randomness is. Okay? So so you can do this. You can do this naturally in two dimensions, and so you see that there is obviously there must be some sort of stable objects that are stable, under random perturbations and are also attracted, are attractive by the dynamics. So the dynamics is attracted to a few of the arrangements of these side branches like that. So I cannot make a more rigorous statement than that. This is not really understood what's going on, but at least the picture says that this is actually possible in the models too. All right. So the others are three-dimensional. There is no randomness as of yet because we exploit symmetry a lot. So you just see a few movies. So you see that how the ridges have developed and branching instability and so on. And then next picture. All right, so next picture is one of our biggest snowflakes. So you see how again, ridges develop. Also they're too small to see here, but they're on either side of the ridge, there are little canals, which we call flumes. Okay, so some of these side branches are actually kind of sandwich plates. Others are not. This is very common in snowflakes like this, which are just, this is really about, let me stop here. So the previous picture was kind of borderline picture. Just the parameters were chosen just on the boundary between the snowflake starting to grow in the third dimension. That's why the picture was so interesting. This picture has, in this particular case, the parameters are chosen so the picture has a very large preference for growing horizontally. All right? And in this case, you invariably get this sandwich instability and the sandwich plate of this type. All right? So all the interesting structure is inside, except that you have these very fast processes occurring on top every now and then, including circles. Completely surprising. So you have this sort of, circles appearing on top. So this is an example of a column, all right, a preference for growth in the third dimension. And then when you see the background changing, I changed the parameters so that now there is a preference for growth in the horizontal direction. All right?
But you can, so can you get capped columns
without that?
changing
No.
the parameters?
No. Without changing the parameters, we could not get a capped column. So the capped columns are almost certainly the result of a changing environment indeed. All right? So, so that's what it is. That's how the capped column forms. And yeah, we could never get it otherwise. So anyway, the fact that this column looks very, very much like columns in nature, capped columns in nature, kind of almost explains it. So here is a picture where the environment doesn't change, but nevertheless there is, in the middle of evolution, something happens having to do with how diffusion field about here organizes itself. So the snowflake looked like a typical snowflake, but all of a sudden started thickening. And you have no more, although you have a lot of structure inside, you have no more structure on the outside. Right? So this also starts growing very, very slowly, as you see. So that's it. Thank you very much. Questions? Yes?
In your two-dimensional movie there, you had this
Yeah.
symmetry, but
Right,
not quite, which
right.
sort of felt really like a real snowflake.
Right.
Do you get that in the three-dimensional?
Yeah,
without symmetry?
Almost certainly you can. We just haven't done that yet because it requires a lot more programming than, yeah. We have not done that. So the question of randomness in the three-dimensional simulation is a future work. It's a very natural next step, but you know it takes time. So you know what you do is you either sit down and prove theorems, or you sit down and program for several months, and you know one has to find a balance between the two. But yeah, I mean it's definitely, that's a very natural next step. I mean, I would be shocked if something very similar doesn't happen. All right. Of course, you have to introduce randomness in a different fashion. The way we did it in two-dimensional case doesn't really make sense. So instead of varying mass, it's perhaps better to varying the diffusion speed or something like that. Randomly varying the diffusion speed, which would kind of correspond to fluctuations in temperature. Right?
Well, you could. I guess you could also have the diffusion itself being random. I mean, the rate is the same, but I mean, diffusion is a model for lots of molecules choosing randomly which way to go. So you could actually model that by a random variable.
Oh yeah, I mean, in a microscopic model, you mean? In a mesoscopic model, I don't know how to do that. Yeah, but yeah. Yeah. I mean, there are several natural ways to introduce randomness, and they should be all roughly equivalent. I mean, that's the expectation. But yeah.
Yeah, I mean,
not
you
done
use
yet.
some stability on the
Yeah. Right, exactly. Yes.
So how many parameters does the model have, first of all? Like 20 or so?
About, yeah. So the geometry, the geometry is kind of complicated, right?
Sure.
So the result of a complicated geometry is, complicated set of parameters, well, large set of parameters.
So then the real question actually is, in order to get most of the interesting phenomena, approximately what is the dimension of the space of parameters that you need?
It's not more than about 3 or 4. What you need is you need a parameter which governs a preference for growing vertically rather than horizontally, and you need a parameter which governs the kind of the advantage concave sides have. Those are basically the two basic parameters, and then you need 1 or 2 just to deal with small details. But yeah, so it's not, at the end, the set of parameters is not that big. That determine the majority of the phenomena that I've shown you. If you want the nicest possible pictures, then of course you fiddle with all of them until you're happy. But if you really just want, the basic phenomenology is, yeah.
Which is nice because you'd expect that in the clouds.
Yeah, exactly. For example, what we typically do, we choose a set of parameters and then we vary the vapor density, which is also a parameter, of course. And you see how the picture changes with that. All right? That you can at least understand what it does. All right? So, so that's... Yeah, I would say you need a parameter. If you really want the basic phenomena, you need a parameter that tells you the preference for horizontal or vertical growth, that tells you the advantage that the concave sides have, and the vapor density. So if you vary those three, you're fine, more or less. Those are the first one to vary.
So is it possible to make movies of real snowflakes growing, or is that impossible?
In the lab, there are. But of course, you cannot, if the snowflake is floating around in the air, you basically cannot do that. There is no technology, even in the lab, all right? So, of course, in nature, it's completely impossible. But even in the lab, that's very difficult. You have to fix it somehow so it doesn't grow. So it's a question as whether the fact that the snowflake is fixed influences the way it grows. So, yeah, so they're all made, so they're at the tip of a needle or on the rabbit hair, classically.
But they are somewhat similar, are they?
Yeah, they're similar. Yes. Actually, one of the pictures I've shown you is of this type. Let's see here. So see, this was grown on the tip of that one was grown on the tip of something. That's from the lab. It's not. It's an actual artificial snowflake. All right. Actually, in order to make sure that it starts, they often also introduce some electricity. So some static charge would help for the particles to stick. So that is all. I mean, some would consider that cheating, some wouldn't. But that's what they do. They have all sorts of tricks. The snowflakes are actually quite tricky to grow. This was, Nakaya was the first to solve that problem. And Libbrecht does this a bit, but it's very tricky. It requires a lot of time and equipment and fiddling and having the right temperature and having the right upflow of air so they just don't all fall down instantly and all that. So, so it's very tricky. Impurities are also a problem. Not too many, not too few. It's a big deal. Not too many people are actually able to do that. Okay, thank you.